the extraction of kinetic energy from wind has been used for centuries to propel sailing boats and used to pump water and milling grains in windmills. Let's look at how the energy from wind is harnessed to generate electricity by exploring how wind turbines work. We will explore the fundamental science of wind, how energy is extracted from the wind, aerodynamics of the blades, and key components with their function in modern wind turbines, as well as different types of wind turbines. Before exploring how wind turbines work, let's get an understanding of the main enabler for wind turbines. Simply put, wind is the motion of air molecules which consist of 78% nitrogen, 21% oxygen, between 1 and 4% water vapor, and other trace elements. Let's zoom out from a molecular level to see how air is manipulated on a large scale to create wind. The energy that drives wind originates with the sun, which heats the earth unevenly, creating warm and cool spots. For example, a sea breeze occurs when inland areas heat up on a sunny afternoon. The air is warmed and expands, leading to a lower density, causing it to rise and creating less pressure. Cooler, heavier air at a higher pressure rushes in from the ocean to take its place, and wind is created because of the pressure difference. The topography of an area has a major effect on the wind climate. More wind is experienced on the tops of hills and mountains compared to sheltered valleys. Obstacles such as trees or buildings significantly reduce wind speeds. The amount of energy in wind depends on three factors: the volume of air, velocity of air, and mass of air. The power output from a wind turbine is given by the expression P equals half Cp times rho times A times U cubed, where Cp is the power coefficient, and we will talk about this in a bit. Rho is the air density, A is the swept area of the rotor, and U is the velocity of the wind. There exists a theoretical maximum of the power coefficient known as Betz's limit. Betz's limit is 59.3% and is derived from the principles of conservation of mass and momentum of the airstream flowing through an idealized actuator disk that extracts energy from the wind stream. A higher efficiency is not possible due to the fluid mechanical nature of wind power that requires the continuous flow of air in motion. Historically, power output of a wind turbine has increased with the hub height and rotor diameters, but there are some engineering limitations. The limit of the size of wind turbines at present is determined by the problems in transporting the large blades and pillar components, the size of the cranes required to erect the turbines, and the cost associated with this. A solution to some of these problems is to build the blades and pillars offshore, similar to oil rigs. Modern turbines use sophisticated aerodynamic principles to capture the wind's energy most effectively. Turbine blades are shaped a lot like airplane wings or propeller blades, using an airfoil design. Blowing air passes around both sides of the blade. Because of uneven air pressure distribution, pressure is higher on one side of the blade and lower on the other, and a lift force is generated, which acts perpendicular to the direction of the wind and causes the blade to rotate, starting the energy generation process. Now that we know how energy is extracted to the wind turbine, let's look at how individual components function to ensure the operation of a wind turbine. A wind turbine consists of a tower, a nacelle mounted on top of the tower, and a turbine rotor. Within the nacelle are several components responsible for converting the wind energy into electrical energy. The components inside the nacelle includes a gearbox, generator, transformer, and control systems. The rotor converts the kinetic energy in the wind into mechanical energy. The rotor contains a hub and blades which is connected with mechanical joints. The rotor hub is manufactured with casting and made from spheroidal graphite iron. Modern wind turbines mostly have 3 blades. The ideal material for blade construction must be low density, possess high strength, fatigue resistance, stiffness, and damage tolerance, with a low cost. Materials used for the shell of wind turbine blades are typically made of glass fiber reinforced polyester combined with a resin matrix to produce a composite. The upper and lower shell are supported by shear webs and bonded on the leading and trailing edges with adhesives. Modern blades taper from the root to tip to reduce drag at the faster moving tip and have a high aspect ratio. The blades also twist from the root to tip to improve the aerodynamic efficiency. Mechanical power from the rotor is transmitted to the generator through a transmission system, which typically consists of the rotor shaft, mechanical brake, and a gearbox. The gearbox of a wind turbine converts the slow, high torque rotation of the aerodynamic rotor into a much faster rotation of the generator shaft. The low-speed rotor shaft connects to the gearbox to step up to a speed that's suitable for standard induction generators. The low-speed shafts are rotating at speeds between 48 and 12 rpm, and gear ratios between 1 to 31 and 1 to 125 are generally required. A mechanical brake is located on the high-speed shaft which connects the gearbox to the generator. Mechanical brakes are applied as a backup method of keeping the turbine stationary for maintenance, or in the case of emergency situations such as extreme wind gusts or excessive rotational speed. The high-speed shaft connects to the generator, which is an electromechanical component that converts the mechanical power into electrical power. Generators typically have a stator, a stationary housing with coils of wire mounted in a certain pattern, and a rotor, the rotating part of the generator. When the high-speed shaft rotates, electricity is generated due to electromagnetic induction. Because the wind's direction and speed are ever changing, a control system is necessary to ensure the optimal operation of wind turbines. Control systems in wind turbines are used when stall occurs on the rotor blades when the wind speed exceeds a certain critical level to maximize power production and reduce structural loads on the mechanical components. Pitch control allows for the rotation of each blade about its own axis. Active pitch control means blades can be quickly turned away or into the wind as the power output becomes too high or too low. When the wind exceeds a certain threshold, the blades rotate to a specific angle of attack and stall occurs, eliminating the force of lift and decreasing the speed of the blades. Pitch bearings are interposed between each blade and the hub to allow the blade to be rotated about its axis. A yaw-controlled wind turbine has a yaw drive, which is constantly rotating the nacelle to get as much air through the rotor disc as possible. In order to apply the correct control movement, the wind parameters must be measured. An anemoscope and a wind vane are used to detect immediate wind status. When the operating status changes, the anemoscope and wind vane send a signal. The signal is diagnosed, processed, and an output signal is sent to the yawing system, pitch control system, and the mechanical brake, which changes the operating status of the wind turbine accordingly. The tower and foundation mainly provides support and height to the electric power generating nacelle and rotor, with the tower raising the nacelle and the rotor to a position where the wind has higher speeds. Special consideration must be given to buckling and the first mode natural frequency to avoid the excitation of resonant tower oscillations caused by rotor thrust fluctuations. The vast majority of wind turbine towers are constructed from steel and towers have a very modest taper. Slab, multi-pile, and monopile foundations are used to provide support. Vertical axis wind turbines has the advantage of generating power from wind that comes from any direction. Generally, they are not efficient enough to compete with horizontal axis wind turbines, both in terms of power generation and economic feasibility. Offshore wind turbines are becoming more popular as offshore mean wind speeds are higher, wind turbulence is low, and large areas are available for wind farm development with limited environmental impact. General Electric's Haliade X offshore 12 megawatt wind turbines are the most powerful offshore turbines. Siemens Gamesa is a newly launched 14 megawatt offshore wind turbine aiming to conquer the Haliade X. Wind turbines are a clean and sustainable source of energy with relatively small amounts of greenhouse gas emissions, caused mostly because of the manufacturing and transport of the turbines and blades. The intermittency of wind, noise pollution, and the initial cost of setting up wind farms are the major drawbacks. Nevertheless, wind is a renewable energy source that can be utilized in conjunction with other renewable energy sources to move towards a greener planet.